Welcome everyone. My name is Timur Kristóf. I work for Valve at the Linux open source graphics drivers group. And today I am here to talk to you guys about how mesh shading is implemented in Mesa. So everyone saw Ricardo's talk, I hope. But just in case somebody didn't, I'm going to do a very quick recap of mesh shading. The good part is that you get a whole new programming model with lots of flexibility, lots of power. So you can do geometry processing and you can process very highly detailed scenes with many vertices, many primitives. The bad side is that it takes a lot of effort to integrate into your applications. And the ugly part is that the new API is quite low level. So you have to do a lot of work to match the performance which you would get from the existing traditional pipeline. And the main thing, as Ricardo already said, mesh shaders are compute-like. Basically, instead of just passing through some input vertices, they can create vertices and primitives. And this eliminates some bottlenecks from fixed function hardware like input assembly and tessellation. Also, the sad thing is that it's not suitable for tiling GPUs, at least the current spec isn't. But as far as I know, Kronos might be working on something. Anyway, so this is how the mesh shading pipeline looks like, but I wouldn't recommend anyone to do this. So this just has a mesh shader and a fragment shader, but most of the performance you can get by adding a task shader to your pipeline. So I would recommend also using a task shader. And task shaders and mesh shaders both work in workgroups, similar to how compute does. And they feed directly into the rasterizer, which then rasterizes them the same way as you would get in a traditional pipeline. So mostly, Ricardo didn't really talk about the task shaders that much. So with a task shader, you basically have to process meshlets. So one task shader invocation usually processes a whole meshlet. A meshlet is a collection of vertices and primitives, usually like maybe 128 or 256 vertices and or primitives. So each invocation of a task shader can decide whether to render a specific meshlet or not. And then it launches mesh shader workgroups for the meshlets which should be visible. And in the mesh shader, the whole workgroup is responsible for one meshlet. So you can already see here that one invocation in the task shader mostly corresponds to a whole workgroup of the mesh shader, which means that if you implement some coarse culling in your task shader, you can avoid launching mesh shader workgroups entirely. And that's where you can get most of the additional performance from. And in the mesh shader, each invocation can process any number of vertices and or primitives in the programming model. That's not exactly true for the hardware though. I will show you later how that works. In a nutshell, the task shader answers the question, how many mesh shader workgroups do you want? And then it can have an optional payload output. And the mesh shader then takes that and feeds something to the rasterizer directly. And every detail about what kind of inputs you use, where do you get your inputs from, that's all up to the application. So there are two main use cases. One is meshlets, which we already discussed. And the other is procedural geometry, which means that you can write an application which generates all of its geometry on the fly, which means that you don't have to have any memory access at all. So if you have a mathematical formula which describes some shape, you can implement that formula in mesh shaders, and then it will just render without any inputs. So in the task shader, Ricardo already talked about this a little. You can do geometry amplification, level of detail selection, coarse culling, which I highly recommend. And also, if you want to use task and mesh shaders, I highly recommend that you replace your compute prepasses with the task shader. So if you already have a compute prepass, which gets rid of some primitives, that means that you basically duplicate some of the work. So I don't recommend that. I recommend that you replace that with the task shader. And in the mesh shader, if you are generating a mesh from some inputs, you can do per triangle culling. And as mentioned before, you can procedurally generate some shapes. So let's get into the actually interesting part. How does this all work under the hood? So let's pop the hood open and look inside. So we started this work in September. When we started, there was no cross-vendor extension, only an NVIDIA-specific one. There were no test cases, no CTS, and no apps. We have an NV sample application, but that's it. So I had to start from scratch, and we made some good progress. So by the end of last year, we already had mesh-only pipeline support in Mesa. And earlier this year, we merged task shaders. And of course, by now, we also have the cross-vendor extension that Ricardo was talking about. So the first thing that you have to consider, what can your hardware do? And how can you map that functionality to the programming model? And for example, one question is, like I said that according to the programming model, the mesh shader feeds the rasterizer directly. But what does that actually mean? Where does the output go? So for NVIDIA, it uses a shared memory-like thing. For Intel, I guess it's URB memory, but there are some Intel people here who I think know better than me. For AMD, it's something called the export space, because we use so-called export instructions to output them. So you might have heard NGG in some conversations online. So it's the hardware stage on AMD hardware, which is responsible for all geometry processing. And it has some pretty strict limitations compared to the programming model that we showed you before. So on AMD, one SIMD lane can output only up to one vertex and one primitive. And each workgroup only has up to 32K shared memory. And it only has a one-dimensional workgroup ID. But this is in contrast with the program. So this is the illustration. Like each lane outputs just one vertex, just one primitive, and that's it. But in the programming model, any shader invocation can write any vertex, any primitive. They have to have up to 48K shared memory per workgroup. And the programming model has 3D workgroups, not one-dimensional. So it looks like this. Each invocation could theoretically output basically anything. I hope that the colors are visible. So how do we implement this? And this is where it gets really messy. So we have this thing called LDS, also known as shared memory. So the implementation basically lowers each output write into a shared memory write. And then at the very end, each shader invocation loads the actual output from shared memory, or LDS, and then exports it. And this is pretty tough because you get a lot of overhead from writing to shared memory and reading it back. So we have an optimization which avoids this. So if you write a mesh shader and you use the local invocation index to address your outputs, then this is not necessary, because in that case, the compiler can prove that you only write one vertex and one primitive in your shader. So in the general case, of course, you can think about, like, if you can have only one vertex, only one primitive, that means that what happens if you specify a workgroup size which is smaller? So let's say that you have a shader. You say you have 32 invocations in your workgroup, but you want to output 128 vertices. And on AMD, that means we have to launch a ver group size of 128, where the first 32 invocations will do all the work that you actually coded in your shader, and the rest are just sitting there unoccupied, doing nothing, just waiting for the other ones to complete. And this is pretty wasteful, so I recommend that when you are writing a mesh shader and you want it to perform well on AMD, you should match the ver group size to the maximum outputs. I mean the maximum number of vertices and primitives, so that you don't get that ugly red unoccupied area. So that's it for mesh shaders. Those are the main pain points when implementing them. How about task shaders? And there are some interesting considerations here. So task shaders need to be able to dispatch mesh shader workgroups. And they need some mechanism for implementing the payloads. And of course, we should allow them to run in parallel with mesh shader invocations to get optimal performance and occupancy from the GPU. So how do we do that? So when we started working on this, I think last year, we were having some interesting discussions about what can the hardware do, what can we use to implement all of this. And our first two idea was that we could abuse the tessellator and basically run that in points mode or something, and then we would get as many invocations as we need. But that sounds like we are just reintroducing the bottleneck that we wanted to avoid in the first place. So we didn't actually do that. The second idea was, well, we could implement our own compute prepass in the driver, but then that's also problematic because it has an extra barrier. So what ended up happening is that AMD has a firmware-based solution for all of this, and the other manufacturers seem to just abuse the tessellator. At least that's how they explained it to me. So what does this actually mean? What is this firmware-based solution? And this is where it gets really difficult and interesting. So you saw the graph about the pipeline, and in there, task shaders are just regular old graphics shaders in a graphics pipeline. Well, the problem is that AMD requires them to be executed on a different hardware queue, which is, they call it the async compute queue, or ACE for short. And so most of the difficulty in the driver implementation comes from trying to pretend to the application that you just have one queue, the graphics queue, where you execute everything. But in reality, in the driver, we actually have to submit the work to two queues at the same time. So how does that actually look like? So we have this async compute queue, which I just abbreviated as ACE queue. It has some command which executes the task shaders. And running in parallel with this, you also have the graphics queue, which executes the mesh shaders. And this means that there is an implicit wait between the two queues. So, of course, mesh shaders can't be launched until the task shader decided how many of them you want to launch. So this task mesh dispatch on the graphics side, it needs to wait, obviously, for the other dispatch on the compute side. And of course, if there is no room to launch everything at once, that means that the compute queue also has to wait for the graphics queue. And this leads to synchronization issues. But first, let's see how this works. So you get a dispatch on the compute queue. You run some workgroups of task shaders. In this example, you can see it's 2. And they write to a location in VRAM, which is called a draw ring. How many mesh shader invocations do you want to launch? And in this case, they launch N and M workgroups of mesh shaders. And if the application also uses payloads, there is another ring buffer, which we call the payload ring, which contains all the data, which is up to 16K per workgroup. And then the mesh shaders read from the same location in VRAM. So, as I said, the main issue here is synchronizing the two queues. And let's look at why. So, I said there is this implicit wait. But what happens if you also have a transfer operation and a barrier? So since the application only sees all of this as just one queue to which it submits all work, it might have a transfer command and a barrier. And then, well, in this drawing it seems to be fine. But what happens if the compute queue doesn't have any work before that and starts to dispatch earlier? So what looks like there is some problem because it doesn't wait for the barrier, right? So you got a synchronization bug, essentially a race condition. So how do we solve this? Essentially, we have to implement some explicit synchronization between the two queues. So essentially, we emit a packet which writes to some piece of memory. And on the compute queue, we have a packet which waits until that is written. So that's how we solved the synchronization. But then, what happens when multiple processes use this feature? And this is an interesting thing, because up until now, everything seemed straightforward. And we had a working implementation, but we noticed when we run the CTS tests, they randomly hang the GPU. And we couldn't see why, until we realized this. So when you have two applications which use this mechanism, obviously, if they are ordered in the correct way, then there is no problem. But the kernel actually doesn't give you any guarantee between the two submissions. So you submit some pieces of work to the compute queue, some pieces of work to the graphics queue, and the kernel might decide to swap the order. It can do that. It doesn't promise you that it doesn't do that. So in that case, you get a big deadlock. And well, how do we actually solve this? And it turns out this is not possible to solve in user space. So the proper solution is called gang submit. It's recently merged into the kernel. And what this means is that you get one submit for both queues at the same time. And the kernel is now aware that these belong to the same job, basically. So it schedules the two jobs together. And this means there can be no mix-up between the different applications. The drawback is that this is not available in any kernel which is released yet. So you can't upgrade your kernel and you can't make it work. So until this happens, we have disabled this feature unless you have this environment variable here. So you can run a mesh shading app using RADV perf test XMS, which is implemented using schedule dependencies instead of gang submit for now. We hope this will change soon when actually the kernel releases this feature. So I talked about a lot of things, but where can you actually find the code in Mesa? So we have a lot of driver-specific NUR-lowering passes. So now, these days, our philosophy in RADV is that we don't implement I/O directly in the compiler, but instead we implement all of it in NUR-lowerings. So we have a couple of these. And of course, there needed to be significant refactoring in RADV to handle these two submissions at the same time. And there is one last thing I'd like to show you, which is the NVIDIA CAD scene demo application. So this is basically an app which shows some really heavy geometry. It has 32 million triangles in total and 16K draw calls, which is, I think, a lot. So I'm going to show you this demo now. And it fits. Okay, that's great. So basically this app shows you how to implement task and mesh shaders. It has examples for the shaders and it's very configurable. So you get various settings about all the parameters that we discussed earlier. So you can choose to regenerate the meshlets. Like you have a number of how many vertices you want in your meshlets, how many primitives, etc. And then you can select whether or not you want to execute with mesh shaders or with the classic pipeline, etc. So now it's VK standard, but now let's switch it to the mesh shader extension. And it's very helpful. It tells you the frame time also. So you can see it's 14 milliseconds now. And with just the standard, it's, well, also around the same. So this would already indicate that you don't automatically get good performance just because you wrote a mesh shader. But when we start tweaking these, like let's say we want 128 vertices and 128 primitives. And then it's already a bit different. You can also tweak like how many meshlets do you want each task per group to process? And what is the minimum number of meshlets for each task shader? And so we can play around with this a little bit. I don't actually remember what was the most optimal combination. So I'm just showing that there is many different possibilities here. And also it has various other preferences. So you could select to compact the output. You could say, let's use per primitive culling. And now you see it performs a little bit better. So it has endless options. I don't want to waste your time on all of this. But if you guys are interested in mesh shading, I highly recommend looking at this sample because it has everything, basically. So thank you very much for your attention. And if you have some questions, now is the time to ask.
So implementing the task shaders on the compute pipeline, won't that interfere if you have long-running compute tasks running from the application side?
So the question is, because the implementation runs task shaders on the compute queue, does that interfere with whatever the application itself is running on the compute queue? And the answer is no, it doesn't. It's basically a different job submission. So both jobs run in some order, depending on how the kernel schedules them, but they shouldn't interfere.
But you can have really long-running compute.
Well, let's hope that the kernel scheduler does the right thing and uses the proper queue, which doesn't have the long-running job. But the application can't really control that.
But if the application saturates the compute queue,
yeah, that sucks.
Now you're out of space.
Yeah. So sorry, I will repeat. So the question was, what if the application already saturates the compute queue? And I replied, yeah, that sucks. Then that means you will have to wait until that work is done.
To get a timely answer to this, on AMD we have multiple compute queues. So we could always decide just to hide one of them so that application can do anything.
Yeah. So Buzz says, just repeating for the stream, that AMD has multiple compute queues. So one solution for this could be that the driver hides one of them from the application.
Hello. What can we do if an application uses a suboptimal mesh shader configuration?
Question is, what can we do if the application uses a suboptimal configuration? Well, the honest answer is not much really. So the mesh shader is intended to be a low-level tool, which means that we push all of these decisions to the application. And if the application makes a bad decision, that means it will perform badly. Sorry to disappoint.
So in both presentations, so it was mentioned that the mesh shaders are not ideal for tiny GPUs. Could you just be like more elaborate about like why they don't run?
Okay, the question is that why are they not optimal on tiling GPUs? And Well, I can only speculate. You would have to ask somebody who works on a tiling GPU to give you an accurate answer. But according to my understanding, the main issue there is that they don't behave well with binning. So the problem is that one mesh workgroup could output vertices basically anywhere. It could have any position. And that would cause issues with the binner, because it would really prefer if all of them would be in the same tile, but they are not. I mean, for more details, please ask somebody who works on a tiling GPU. We have plenty of people here who work on tiling GPUs, right?
What is an example of a tiling GPU?
What is an example of a tiling GPU? Well, ARM, Qualcomm, Imagination. So almost all or all mobile vendors are tiling GPUs. Well, if there's no more questions, thanks.